So just a little bit of context in this domain, this criminal justice domain. So here we're talking about a pretrial decision-making context. And in the United States, shortly after someone is arrested, 24 to 48 hours after someone's arrested, a judge has to make a high-stakes decision about whether or not that individual is detained or released pending future court dates. So this is a tricky decision. There are complications on both sides. On one side, the state has an interest to ensure that people who have been charged with a crime don't commit more crimes during this pretrial period. And on the flip side, this is all done under a presumption of innocence. Relatively little evidence has been brought at this point. And so we want to make sure that we're not detaining people without real cause. Because detaining people, this can have all sorts of deleterious consequences. For example, they'll be disconnected from their family, they're likely to lose their job, they might take a plea deal that they might not otherwise have taken. So all of these pretty harsh consequences in this high stakes moment. So because of this, there's been a push now to use algorithmic decision-making to guide these human judicial decisions. And now I'm going to abstract away a little bit. I'm going to come back to this example, but I want to abstract a little bit away and just say that we're thinking of a broad class of prediction problems where these algorithmic tools are being used to guide those risk assessments. And I'm going to make two key assumptions. So the first assumption that I'm going to make, these are risk assessment problems. The first assumption I'm going to make is that we're predicting the right thing. And so this is in contrast to what we heard from Ziad's talk, where there the whole problem of fairness is that we weren't predicting the right thing. The algorithm was predicting something like future medical expenses. In reality, what we cared about was something like health. And here I'm going to ignore that problem, and I'm going to say we're in a best case scenario where we're predicting the right thing. And so this means that we have the true label Y. And that really means two separate things. The first thing is that we're measuring what we think we're measuring. So if we're measuring crime, we're actually measuring crime. We're not measuring arrests or convictions. We're actually measuring crime itself. We can never do that. I mean, that's almost impossible to even think about what that would mean. But I'm going to assume that we have it right now. And the second thing is, in many cases on training data, we only get to see what happened conditional on a particular course of action. So here we might only see, did somebody go out and commit a crime, conditional on being released. And so here I'm going to assume that we have these counterfactual outcomes in our training data. So you can think that the training data was generated through some sort of randomization process or whatever it is, but we can actually train exactly the thing that we want to train. So that's my first big assumption. Now, the second big assumption is that basically I'm going to assume that there's no machine learning here and that there's no estimation error. So we've solved all of our problems. We have exactly what we want to predict. We have that perfectly. And there's no learning in the sense that we've already solved that and there's no estimation error. So formally, what does that mean? That means I have exact access to the conditional probability of Y, this thing that I'm trying to predict, given my available covariates. So I'm not an oracle in the sense that I know exactly what everyone is going to do. I don't know if I were to release somebody, would they go out and commit a crime, would they not go out to commit a crime? I don't know that. That's too much. But what I do know is conditional on the data that I have. So I might see somebody's age, I might see their previous criminal history, I might see all this stuff about them. Conditional on that, I have a perfect risk estimate. So this really just means there's no, again, estimation error, conditional on my covariates. Okay, so I don't believe either of these assumptions, obviously. These are both quite strong assumptions. The first one is particularly strong. The second one is perhaps more reasonable if I have a lot of data, but it's still a reasonably strong assumption. But the argument I'm going to make now is even in this perfect world, we see all sorts of funny effects when we try to formalize our definitions of fairness. So it's not, again, that I believe either of these assumptions, but even when we have this best case scenario and when we've assumed away a lot of the problems that we tend to focus on, even then we're left with these pretty big issues with the formalization of fairness. Okay, so now let's again abstract up one level and think about this decision-making process. So how does this work? We have features. So again, this might be someone's age, it might be someone's criminal history. We make some sort of prediction, and then we make, based on that prediction, we make some sort of binary decision. I'm going to use binary for simplicity. In general, you can make more complex decisions. And that decision itself can depend both on the prediction, the estimate that I get out of my model, and then also the features that I'm using. And so in this sense, that prediction box is just kind of thrown in. I don't actually need it, but I'm drawing it here to highlight the role of prediction in this algorithmic decision-making process. Okay, so now let's think about this prediction box. So again, by one of the assumptions that I made, we have this thing perfectly. The prediction, given my features, is just perfectly set. So there's nothing to do here. I put it into my black box, my blue box here, and I get my answer of the conditional probability of y, of whether or not someone is going to go and reoffend, based on all the information I have of them. Good. So just geometrically, what does this look like? So this is kind of the key slide of this talk. Once we understand this figure, really everything else will fall into place. So let me go through this a little bit slowly. So let's say I have my I have my model, and for simplicity, we'll just think of a logistic regression model, something very, very simple. We have our feature set, so we have a handful of features. We have our logistic regression model, and now I'm going to use this to make predictions about everybody in this room. So I've trained it somewhere, and now I'm going to make predictions about everyone in this room, and what I'm predicting is everyone's likelihood to reoffend if released. And the model, we believe, is perfect, conditional on the covariates that I have access to. So I might say 5%, 2%, 3%, 8%. For everybody in the room, I have this prediction. It's deterministic. It's just a number. It's come out of my model. There's no randomness there. And now I can plot the distribution of those predictions over the entire population that I'm considering. So over this room. So here I might have something like 50 predictions, and I can plot the distribution of those predictions over the entire room. In general, I just have my population that I care about. I have my model, which I've pre-trained somewhere else, and I'm just plotting the distribution of those predictions. So that's what I'm showing here. This is the distribution of predictions over the population. Again, there's no randomness, but it's a distribution of predictions. The horizontal axis is that risk estimate coming from my model, and the vertical axis is just showing that distribution. So it's just a density over all of these things. We can just think of this as a histogram over my distributions. Okay, so now if I change my features that I use to make this prediction, what's going to happen? Well, if I don't have very many features, if my features aren't very predictive, what is this picture going to look like? The idea is, what is this picture going to look like? What's going to happen if I don't have very many features? It's going to look like a point mass right at the mean. And why is that? Because everybody looks the same under this very, very simple model. So what does that mean? That means everyone is going to have a 10% prediction, something like that. Now, the flip side is if I have a super informative model, what is this picture going to look like? Excuse me. It's going to look bimodal. It's going to be high variance where lots of people are close to 0 and lots of people are close to 1. If I have very, very good predictions, I can almost perfectly separate the population out into these two different groups, people who are close to 0 and people who are close to 1. But regardless of my choice of x, I'm going to have the mean of this distribution will be the same. So no matter what covariates I use to make my prediction, the mean of this risk distribution will be the same, but the variance can change depending on how I choose that covariate vector. Okay, so now we're actually basically done. Once we have this picture in mind, and I know I was going through this, I was trying to go through this a little bit slow and trying to be pedantic about it, because really this is the whole picture, and now we just follow the implications of this geometric intuition to get some surprising results. Okay, so what is this going to look like? So first, we have to know how are we going to make decisions based on that picture that I just showed. Well, one very simple way, and again, this goes back to Ziad's talk, is that we can just draw a line, and we say everyone above that line, we do something for, everyone below that line, we do something else for. So everyone above, in his example, we automatically enroll into this VIP program, into this more high-touch care, and everyone below that line, we just go the standard procedure. Right, so a very simple thresholding. And in the criminal justice context, what does this mean? This might mean we detain everybody who is estimated to be sufficiently risky and release everybody else. This type of policy has the nice property that it's efficient in the sense that if I want to detain a certain number of people, this thresholding will pretty clearly maximize public safety conditional on that level of incarceration. Okay, so it's perfectly efficient in this narrow sense of optimally trading off between detention and public safety. Now, but it's not the only way that I could make a decision. Another way I can make a decision is if I have two different groups, here denoted by my red group and my blue group, and I have two different thresholds for individuals in each of these two different groups. So here, I might say I have the the right-hand side of the room and the left-hand side of the room, this is arguably a non-random split of the population. If I have two different groups, I'm going to have two different risk distributions. So again, imagine I'm using my pre-fit model to make an estimate of everybody's risk on this side of the room. We'll call this the blue side. And then on the red side of the room, I'm going to do the exact same thing. I'm going to have two different risk distributions. And I could say I'm going to have two different thresholds for determining what to do for these two sides of the room. So anytime I have a non-random split of the population, I'm likely going to have two different risk distributions, and I can treat them differently with two different thresholds. So I can do this in theory. In practice, it's a little bit funny. So this is a double standard, and it raises some ethical issues. So in some cases, we might want a double standard. In many cases, I'd argue we don't want a double standard. And so one kind of econometric way of thinking about why double standards can be problematic is that they're not efficient in the sense that I talked about before, in that here, I've decided to detain relatively low-risk blue individuals. Because that bar is lower for the blue group, I've decided to detain relatively low-risk blue individuals. If I were to switch to a single threshold, irrespective of the group membership, then I could detain fewer people and still have the same public safety benefits. So I think we all probably have some intuition for why double standards can be problematic. But here, again, I'm just giving a very kind of an econometric way of thinking about why these double standards are problematic. So here there's a term called taste-based discrimination. So here, many economists would say that we're acting in a way that expresses taste-based discrimination because we're willing to lose efficiency to satisfy this taste for discrimination against the blue group in this example. Okay? Good. So now, that was just kind of a quick framing of how I like to think about algorithmic decision making. So now let's get into the actual formalizations of fairness that have been proposed. So there are many, many formalizations of fairness that have been proposed over the last few years. And I want to start with one that's quite common, that I'm going to call classification parity. So one of the things about this field is it's still relatively immature, and so the names keep on shifting. So classification parity, this is the term I'm going to be using. Probably you've seen this go by many other names. And so what does this mean? It means that if I have an algorithm, I'm going to assess its fairness by first picking my favorite error metric. Maybe this is false positive rate, maybe this is false negative rate, maybe this is AUC, my favorite error metric. And I'm going to ask the extent to which this metric is the same across groups in my population. So in many cases, this is race, this could be gender, this could be whatever group I want, but I'm going to compare the value of that error metric across different groups in my population. So let's talk about false positive rates. This is the one that's received quite a lot of attention. So again, I know we're coming back from lunch, so let me remind you what false positive rate means. I also have to remind myself too, so I'm going to phrase this in my criminal justice example. What does this mean? It means among people who would not have reoffended, what proportion are deemed high risk by the algorithm? Among individuals who would not have reoffended, what proportion were deemed high risk by the algorithm? Okay, that's what false positive rate means. So a positive is you're classified as high risk, and it's false in the sense that we're assuming here we're looking at the proportion of people who would not have reoffended, but they're still deemed high risk. So it's a false positive. Okay, so now this is the statistic that received a lot of attention in this article that I posted earlier. And here, so we redid the analysis, and these are the numbers. They corroborate the numbers that they presented. And let me just repeat them for you. So among black defendants in this population, and this is a particular population of defendants in Broward County, Florida, among black defendants who did not ultimately go on to reoffend, about a third, 31%, were deemed high risk by the algorithm. In contrast, among white defendants in Broward County who do not go on to reoffend, about 15%, about half as many, were deemed high risk by the algorithm. So this is a pretty stark difference. And let me just see, how many people just feel viscerally bad when you see this number and you're like, something must be terribly bad about this algorithm? So I felt the same way. Now I'm going to try to persuade you in 5 minutes that this doesn't mean quite what we think it it means. And so the point here is that our intuition about these numbers, they really can lead us astray unless we get into the details. So let me see if I can pull this off in 5 minutes. Okay, so first let's abstract this a little bit, and we have our two groups, the blue group and the red group, and they're sorted by their risk. So the numbers underneath them, these are my perfect estimates of risk for each individual in the population. Because they're two different groups, they have different distributions of risk. That distribution of risk is not something that's inherent to group membership. It's just like the same way that if I said the left-hand side of the room and the right-hand side of the room, there's not something inherently riskier about the left-hand side of the room compared to the right-hand side of the room. They're just different distribution of covariates, and so we're going to have different distributions of risk. So I have my two different groups. I'm going to draw a line. Again, this was the sort of efficient way to make these decisions, and in many cases, it's arguably one of the only ways to make a constitutionally legitimate classification decision, given our risk scores. And so we have those to the right of that line are detained in this example. Those to the left are released. Okay, now let's compute the false positive rate for this blue group. Again, so I'm going to ask for audience participation in a minute, so you have to pay attention. So again, what does false positive rate mean? This means among people who did not go on to reoffend, how many were deemed high risk? Among people who do not go on to reoffend, how many were deemed high risk? Well, I can just add these probability ups. It's not quite so simple, but intuitively I can do this. This is the probability that they're gonna reoffend. I can look at 1 minus that, the probability they don't reoffend. I can just kind of add these things up, and I can see how many of those people are to the right of that dashed line. And when I do this, I have 2 out of 8. So 8 people in this population on average don't go on to reoffend, and of those, 2 of them are to the right of that line. Okay, and so I get a 25% false positive rate. Okay, so now you have to think for a minute. We're going to switch the red group. So the red group, remember, is shifted over. It's that blue group shifted over. So what's going to happen to the false positive rate of the red group? So what's going to happen to the denominator on the bottom of this fraction? Is that denominator going to be bigger or smaller when I'm talking about the red group? So in the red group, do more people reoffend or do fewer people reoffend? So more people. So no, there are no trick questions here. It's just like, it's a little bit, the arithmetic itself is what's tricky. So it's a higher risk group, meaning more people are going to reoffend, meaning fewer people are not going to reoffend, so that denominator is smaller. And it's not mathematically has to be the case, but these distributions have the property that of those people who do not go on to reoffend, more of them are to the right of that line. Why is that? Because the entire distribution is shifted to the right. So in this case, I have a higher false positive rate for this red group compared to the blue group. And why is that? Well, I mean, it's always tricky to say why is something true, but here what's going on is that because there's a higher base rate for this red group, because I've shifted this group over, that also corresponds to having a higher false positive rate in that group. So I draw the exact same line. I'm saying I'm making my decisions only based on risk. I'm drawing the exact same threshold for everybody, but I have a higher false positive rate for this red group compared to this blue group. Okay, so now what's going on here is that false positive rate, and in fact every error rate that you can think of, is an infra-marginal statistic. What does that mean? So our definitions of fairness often concern what goes on at the margin. So this idea that we have a single standard is a statement about the margin. But these statistical definitions of fairness, they integrate over the entire distribution. So they not only care about what's going on at the margin, they also care about that underlying distribution of risk in the population. So in this sense, they're an infra-marginal statistic. And here the idea is that infra-marginal statistics can be misleading proxies for understanding that threshold, which is this, which is arguably this, excuse me, more conventional way of thinking about fairness, at least in the kind of constitutional and social interpretation of these questions. Okay, so now, given this, you might still look at this picture and be like, well, I'm not really convinced, because even if I have to draw a line, and maybe this is like a tough thing, you're like, okay, well, I don't have a lot of good options, I'm going to draw a line, but still this red group feels like they're being harmed because they're subjected to this higher false positive rate. it still feels like something is bad. Now let me push on this a little bit more. So here we have our red group. This is the high false positive rate group, the 40% false positive rate group, and I feel bad about that 40%, and so I'm going to lower that 40%, and how I'm going to do that, I'm going to go out and I'm going to arrest a bunch of low-risk college protesters. So why am I going to do that? Nothing else is going to change. I'm not going to change anybody's risk estimate. I'm not going to change my threshold rule. I just feel bad about that 40%, and so I'm going to lower it by arresting a bunch of low-risk college protesters. And why is that? Because what is our definition of false positive rate? Among people who do not go on to reoffend, the proportion that are deemed high risk. The people, because these are low-risk individuals, none of them will be deemed high risk. The algorithm knows that. But most of them won't go on to reoffend, so they'll all go into the bottom of this fraction. And so here, I can go from a situation where it feels like one of these groups is worse off than another, the red group, and I can make it look like they are both okay now by just arresting a bunch of low-risk college protesters. Now, of course, I'm being facetious here. We're clearly making this red group worse off, and the point isn't even one of incentives. It's not that we believe that demanding that people have equal false positive rates in their algorithm creates all sorts of perverse incentives, although it could. That's not the point. The point is that to understand what these statistics mean, we need to understand the full distribution of individuals in the population. Now, let me also highlight that what's going on here is not a general indictment of the way we do machine learning, in the sense that often when we write machine learning papers, and probably everyone in this room has done the same thing, is you have a bunch of algorithms, your benchmark algorithms and your new algorithm, you have your gold standard data set, and now we just run all of our algorithms on that data set. We get a bunch of numbers, and we hope our new algorithm does better than all of these other algorithms on some metric like false positive rate, like AUC, whatever our favorite metric is. Great, that's what we do. That's conventional machine learning. That's how we advance the field. Now, this isn't what's going on in this example. What's going on in these examples is that we have one algorithm, not multiple algorithms. We have one algorithm, and we don't have one data set, but we have multiple data sets. So in conventional machine learning, we have multiple algorithms in one data set. In this type of comparison, we have one algorithm in multiple data sets. So multiple data sets correspond to these multiple subpopulations that we're looking at. And once we do this, we don't have an apples-to-apples comparison anymore. And so it would be the same way as if I said, okay, here I'm going to write my ML paper, and I'm going to compare my algorithm on one data set, and I'm going to compare my benchmark algorithms on another data set, and I'm going to use those benchmark algorithms. I'm going to select them in a way which is really hard on the data sets that are really hard to perform well on, and I'm going to evaluate my algorithm on a data set which is really easy to perform well on. That would clearly, we would think of that as not an apples-to-apples comparison, and that's exactly what's going on here. Then when we see these different numbers, these different false positive rates, or any error metric that you want to think about, this type of conflation is happening. Because we're varying the underlying distribution of individuals that we evaluate on by cutting the population in these two groups, we can't make the direct comparison anymore, so we lose some meaning there. I think I'm basically out of time, so I'm going to skip this last this last part and just skip to the end. So what is the coda here? So in a sense, the big message is that there's problems when we try to strictly formalize fairness and then optimize against that specific objective. And this, I think, is a theme that came up in Milan's talk as well, that we're clearly familiar with mathematizing these problems and in writing these things in quantitative ways, and I think that all makes sense. I think the problem is when we believe a little bit too strongly in these metrics and we don't think about the greater context of where these decisions are happening. So this is one of the big issues that I see with still this young field of fair ML. And in particular, the example that I showed, even though this is arguably one of the most common metrics for evaluating the fairness of algorithm, this classification parity, it fails to recover what's going on in this very, very simple scenario where everything's perfect, no estimation error, there's no proxy bias or measurement error, we know exactly what we want to predict, and we have no estimation error. Even here, we have all sorts of counterintuitive results when we take those mathematical definitions to fairness a little bit too seriously. So again, the answer, I don't think, is is throwaway math, but the answer is think a little bit more critically about these definitions when we apply them as objectives. And now finally, and I think this is a big point, and it also goes back to both what Milind and Ziad were talking about, of thinking of algorithms as separate from policy itself. So statistical algorithms are often very good at synthesizing information and making predictions about the future. They're very bad about telling us what to do with that information. So if I say, here's an individual, I think they're high risk of failing to appear at a future court date. Well, one decision that I could make, which is arguably unfair, is to immediately detain that individual. Another decision that one could make is determine why they're high risk. For example, maybe they don't have easy access to transportation, and then address that issue. So for example, order door-to-door rideshare service to get them from their house to the court. Exactly the same statistical information is being used, that they're high risk of failing to appear at court, but the intervention, getting them rideshare service or detaining them, are quite different and speak to the way that we think about the equity of this particular decision setting. And so that's exactly what we're doing, for example. So now we're using these statistical algorithms to roll out rideshare programs for people who need to get to court all across the country, again, using that same underlying model, but using it in a way that I think leads to more equitable outcomes. So I'll end with that. If you're interested in reading more about this, check out these two papers. One, which is very much the content of this talk, and the second one is a bit more technical discussion of the same material. And also, if you're interested in some of the interventions that we're doing in our broader work that looks at this intersection between policy and computation, check out what we're doing at the Computational Policy Lab. I'll end with that. Thank you.
Okay, let's take one question for Sharad.
Can you put the slide one back? Yeah, so that people can see.
Yep.
You were too fast. The question is, so you have added an irrelevant group to the analysis, and thus kind of change the meaning of the false positive rate, like you equate it by adding the college students, for instance. The same thing you could do by taking out a subgroup and saying that, you know, this is irrelevant for our analysis, and again change the analysis. That's one of the risks, right? So that becomes then very, very difficult to, like, it's very open to manipulation of the data and of the sampling, I think.
Yeah, so again, I think you're right that, you know, when you have that type of property, it leads to funny incentive issues. And I do think there are actually real world examples where you can point to funny incentive issues happening. But here the point was not one of incentives or one of manipulation. It was really to highlight the fact that the distribution of risk, that underlying distribution of risk in the population, is critical for determining the value of these types of error metrics. And so even very simple changes that are clearly harmful to a group can make it appear that the group is better off. And again, the point is not that I believe someone is going to go out and do that, but just to highlight the fact that that underlying distribution matters.
All right, let's thank the speaker again.
Okay. Hold on one second. All right. It is my great pleasure to introduce our next two speakers who will be speaking together. When Shamli and I were thinking about what kind of speakers we wanted to come to this workshop, we were very excited to target speakers who are doing this actually in practice, who can speak to the actual practical challenges of what happens when you get a little further along from thinking about the algorithm, as many of our speakers earlier have sort of alluded to. So I'm very excited that we've were able to convince these speakers to come and give this talk. So we have two speakers. Noah Dagon has a MD and a MPH degree from the Hebrew University. She is currently the head of data and AI-driven medicine in the Clalit Research Institute at Clalit Health Services. Dr. Dagon is currently focusing on the development and research of data and AI-driven solutions in medicine to promote preventative and proactive care. Noam Barda is an MD with honors, doing his residency in epidemiology and public health in the Clalit Research Institute at Clalit Health Services. Dr. Barda's research focus is at the intersection of computer science and epidemiology, particularly in development and application of machine learning and biostatistical algorithms for disease prevention and treatment. So let me go ahead and load the slides. And let's go ahead and welcome our speakers.
So thanks for the organizers for having us. I'll start and Noah will take over at some point. So first let me give you the setting that we act in, we function in, because it will make the data make sense and it will make the problems make sense. So we live in Israel. In Israel, health insurance is mandatory, and patients get to pick between one of four national organizations. They are called sick funds. They are somewhat akin to HMOs. They are all non-profits. We specifically work in Clalit Health Services, the largest of these four sick funds, established 1911, which for the historically inclined is 30-something years before the State of Israel was established. It is the largest one, directly insuring 53% of the Israeli population. That's 4.5 million current members, and it's a one-stop shop. We basically do everything, ranging from the first encounter someone has with the healthcare system, coming to your primary care physician, and the most specialized sort of care given in hospitals. We are the research institute of Clalit Health Services, called Clalit Research Institute. We are a multidisciplinary group, clinicians, data experts, data scientists, etc. And we have a mandate, I remind you that we are a non-profit, to take that data, and I'll talk about the data in a second, it's quite incredible, and turn it into insights, and turn the insights into policy within the Clalit. So everything we do, the academic part of it is only a side effect. Our mandate is to actually generate policy to aid patients. Our data, well, we have currently 4.5 million members. Going back in the database, we have 6 million. We have both community and hospital data because, like I said, we directly provide most of the services to our patients. We are both a payer and a provider, so we have EHR, medical data, and we have claims data for everything that we don't directly provide. And because we've been digitalized for over 20 years, since the late 90s, Israel was a very early adopter of electronic health records, and we have a low attrition rate, under 2% per year, we have very long-term follow-up of our patients. Okay, one last thing about us, well, two last things are, one, we have been doing this for quite a while, so we already have several models in production, predictions in production, things like preventing readmissions, preventing progression from pre-diabetes to diabetes, targeting flu vaccine outreach, things like that. And last is that recently, thanks to computational advancement, thanks to certain software engineering projects done within the Institute, we have become quite adept in generating prediction models, like good, well-validated prediction models have become something that basically, for single diseases, we can generate within days, sometimes even within hours. And that has led us to trying to tackle the difficulty that now arise. So you have a prediction model, you want to put it into actual use, what are your difficulties? So the one difficulty we'll be discussing is the issue of fairness. There are many ways to catalog biases, unfairness. We opted for this specific categorization, whereby unfairness can stem from biases inherent in the data, it can stem from the modeling process, or it can stem from the way the developed model is used in practice. We'll only deal with the two later ones. In this lecture, we won't be talking about biases inherent in data. Okay, so we're talking about biases that stem from the modeling process. That's the first thing we'll talk about. So as you very well know, prediction models, they aim to optimize some loss function that is almost always, invariably, an average, sometimes weighted, usually not even weighted, over the entire training set. So that would mean, and this is very hard to avoid, that populations that are underrepresented in the training set will receive non-accurate predictions. If I don't have many of some ethnicity in my training set, that ethnicity is likely going to receive non-accurate predictions, and that basically means that the developed model is unfair to minority groups. Now, I said non-accurate, but I didn't say what non-accurate means, and like we just heard, there are many definitions for inaccuracies. So by and large, we can divide performance metrics from predictive models into those that deal with discrimination, which can be global discrimination, the area under the receiver operating characteristic curve, and it can be something that is threshold dependent. We saw sensitivity, we saw positive predictive value, specificity. Those are the common epidemiological names for what we've just seen. And we have the issue of calibration. So I hope most of you, or maybe all of you, are familiar with what we see on the right of the slide. That's a calibration curve. Calibration basically means that the predicted risk equals the actual risk. So if I have 100 people on which I say that they have a 30% risk of some outcome, 30 of them are actually going to have that outcome. Do note that a model can be perfectly discriminatory. It can successfully rank patients and still have horrible calibration because it would underpredict, overpredict, or maybe under at some range, over at another range. So this is a calibration curve, and a calibration curve plots the average predicted versus the observed rate, and we want our predictions to be on the 45% line. So because we only get to see the Y, the actual label, and not the probability, we need some sort of smoothing or binning. But regardless of the methodology, eventually what we want are that the line will sit exactly on the 45% line. And this choice that we make to focus on calibration is something that needs to be motivated. So why calibration? After all, most of what we heard today, most of what you see in the literature is very threshold-based. Well, in medicine, decisions are generally made using absolute risks. If the patient has a risk over something, then we treat. If under something, then we don't treat. If you use a threshold-based metric, that can be justified. It really can, but you need some assumptions to hold. You need that threshold to be constant because you keep referring to performance around that specific threshold. You need it to be widely accepted. One, it needs to be widely accepted between locales. It cannot be different between hospitals, between countries even. And second, you need it not to be subjective. You need different patients and providers to agree on it. And last, it really only fits if you deal with one outcome in isolation, which I'll explain in a second. And I'll tell you that usually guidelines are dynamic. They update over time. And they differ between places, and they even differ, and maybe they should, between individuals. Basically, a threshold, as was alluded to in the previous lecture, is a function of the utilities the patient assigns the different outcome. If I am completely unafraid of receiving a prostate biopsy, but I'm very, very afraid of prostate cancer, then maybe, I should be referred to a biopsy sooner, even when the risk is smaller, because then you'll be maximizing my utility. That's expected utility theory, the basic framework for decision-making in medicine. And last and not least is when we weigh different outcomes, positives and negatives from a single decision, we need the prediction to be accurate at whatever range it is given. Otherwise, the weighting will be off. So The bottom line is we need accuracy across the prediction range, and we think calibration is a very good measure to deal with this. So, like I said, we have a model. It's developed on a training set. The training set has underrepresented groups, minorities, and they suffer miscalibration because that's how models work. They perform not as well on the small populations. This is not a new problem. This has been known for dozens and dozens of years. What's the usual solution? We heard about it yesterday in the ML for Healthcare workshop, that the usual solution is just to purposely oversample the minority groups. We see here the way they dealt with cardiovascular disease prediction in the United States. They had a problem with ethnicities that had very bad performance, so they created the data set, the MESA data set, multi-ethnic study of atherosclerosis, where they purposely oversample minorities. That's a valid way of dealing with this specific problem. This will improve performance on these ethnicities, but usually we don't just want to protect ethnicities. So say we want to protect ethnicities and it's just 5 categories, and we want to protect both genders, and we want to protect age groups. We don't want to be ageist, right? And we want to protect socioeconomic status. We want to protect immigration status. And this is a toy example. Usually you'll want to protect a lot more. This blows up exponentially. And in the middle of this, you have this one subpopulation, in this specific example, Caucasian female of a certain age, of a low socioeconomic status, and the history of immigration, and you have hundreds of these groups. You cannot purposely oversample all of them. Your training set would be, the study would cost more money than your grant would ever cover. So we sought to see if we can observe this specific problem of subpopulation miscalibration in our data set, and whether or not we can propose a solution based on published machine learning algorithms. We specifically chose the issue of cardiovascular disease prediction. This is the oldest prediction task in medicine. It's also the most explored. We took as baseline model the American College of Cardiology, American Heart Association, 2013 pooled cohort equations, which I'll just call the pooled cohort equations to save time. We extracted a population that corresponds to the model. In the Clalit data set, that's 1 million patients, more or less, of the proper age group. These are patients that have not had a cardiovascular event at baseline, because that's how the model works. It's a primary prevention model, and we followed them for 10 years. These are the predictors. If you know anything about medicine, you'll identify the standard cardiovascular disease risk factors here, and we sought to protect the 5 variables which I talked about earlier: age, sex, immigration status, socioeconomic, and ethnicity. So the first thing, let's look at global calibration. Right, this is a very widely used model, and we see that global calibration is great. You see the histogram of predictions at the bottom. At the entire relevant range, the calibration is very, very good. It's directly on the 45% line. The measure we use in this study to represent this is calibration in the large, which is the correspondence of the average predicted and the average observed. We specifically use the odds ratio, which is commonly used in epidemiology, and the optimal metric, the optimal statistic we want to see is 1, and here we see 1.01. Perfect, right? No problem. The model works great on the Israeli population. But what happens when we start looking at subpopulations defined by intersections of those 5 protected variables? This is a density plot. We see that, yeah, the mean is fine, but 20% of subpopulations receive significant underpredictions, and 20% of them receive very significant overpredictions. Look at that long right tail. These are populations that receive on average predictions that are 2-3 times higher than the truth. And do be mindful that we decide on medical care, on giving statins, on giving aspirin, based on this specific model. This is another graph showing something similar. On the x-axis, you see the different subpopulations. So every point is one subpopulation. On the y-axis, you see calibration in the large, but on a log scale, so as to make the deviations around the positive and negative deviations symmetric. So now 0 is the optimal point. On the left side, you see the entire population, and going to the right, the populations become smaller and smaller, and you see you see this very serious deviations. We have subpopulations, this is base E log. We have subpopulations getting times 2.7 what they should be getting. And the predictions, we see under prediction, over prediction, this is not good. And we sought to solve this, and my colleague will tell you exactly how.
Hi. Okay, so after observing that we indeed have a problem, although the overall calibration seems to be almost perfect, the subpopulations really have poor calibration, we try to empirically evaluate whether we can adopt an algorithm previously suggested by Heber, Johnson, et al. To correct exactly that, to correct calibration within subpopulations. Now, this algorithm is a post-processing algorithm. That means that it works on predictions that were already created by different prediction models that can range from simple logistic regressions to deep neural networks, and basically takes those predictions along with the correct outcome and all of the protected variables that are used to define the subpopulations, and then it iterates through the subpopulations, each time identifying a subpopulation for which the difference between the average observed outcome and the average predicted rate is higher than some tolerance rate called alpha in this algorithm, and then it shifts those predictions into the right direction, and basically finishes running after all subpopulations are calibrated to the same under the same tolerance parameter. So we implemented this algorithm on the same data set that Noam has described, and this is what we've received. This is the before and after picture of the distribution of the different calibration in the subpopulations. And when we got these results, we were pretty surprised for two reasons. First, I have to admit that we were pretty skeptical that the algorithm will ever finish running. So although the algorithm does have a mathematical guarantee of convergence, it's like when you think about it, it's not very intuitive to think that once you correct the calibration of a specific subgroup, a different subgroup that has some overlap with the first group will not be, like the calibration of that group will not be damaged. And again, but the guarantee actually worked, the algorithm converged, it stopped running. And the second thing that we're pretty surprised to see is how well it did. So this is all test set data, and you can see that the calibration is much, much tighter around the ideal value of 1. So this is basically means that now all subpopulations have much better calibration. This is the same before-after pictures, but now for the calibration of every single subpopulation. And what you can see here that even for the relatively small subpopulations on the right, the algorithm also performs pretty well, okay? So it really has the ability to correct calibration even for relatively small subpopulations. Now just to dive into 3 specific subpopulations in order to get a sense of what really happens inside, we see the calibration plots, again, the before and after for 3 specific subgroups from those hundreds of subgroups that we've discussed. And what you see is that not only does the plot or the curve shifts into the average diagonal, it also changes its form that it can actually spread across different deciles or quantiles on the diagonal itself. And this is an important issue, so remember that, and we'll get back to it later. In terms of number, I think the results that we were most excited about is that the variance between different subpopulations was reduced by more than 99%, and this is pretty amazing in terms of fairness. And another thing that we were concerned about is that if we will manipulate the calibration, maybe we'll damage the discrimination. So we checked again and again for this model and for others, for other outcomes that we checked, and we saw that this discrimination is indeed pretty constant. Now, it's pretty interesting to think of this process not only in terms of how well the algorithm did in an empirical evaluation, but also what this evaluation can do to inform back the theory. So the first, I think that the most interesting thing that we found is that although the original algorithm suggested that the calibration will be performed not only for each subpopulation, but for each specific quantile within a certain subpopulation. And we initially tried to implement that using deciles as the chosen quantiles. And what we found is that we have a problem of overfitting and intractable running times. So what we did is to choose the quantile that is the entire subpopulation. That means that we move the entire subpopulation. That is called multi-accuracy in this literature. But as a side effect, what we found is that we actually got what we set out to receive in the first place, which is multi-calibration. It's not just that the average group shifted into the right direction, it's that actually we saw in the different calibration plots, the different deciles really shifted into the correct place on the diagonal. That means that we ran multi-accuracy, which is a much simpler model, but we actually got multi-calibration. This was something that was not known in the literature before. And the second interesting thing is the size of the subgroup that was found to be effective in this empirical evaluation. So basically, we want the subgroups to be as small as possible to include as many minorities as possible. This is the fair thing to do. But that risks overfitting at some point. If the group is too large, on the other hand, we basically lose the meaning of everything we do. And in this case, what we found is that an ideal value of something like 5,000 individuals performed the perfect group, because that is basically where the reduce in variance converged, or not converged, reached a plateau of about 99%, and this is where we felt it's good enough. And I'll remind you that we started off with a population of about 1 million individuals, so 5,000 individuals out of this population is really a minority. So this algorithm really sets up to do what it does, really does what it sets up to do, which is correct the calibration even for very small minorities. Okay, so this is about this algorithm. I can tell you that we are very happy with the result as an institute that is responsible to treat patients. And the next thing that we plan to do is to take this algorithm and to add it as a post-processing phase to every prediction model that we create in the automatic prediction tools that Noam has discussed. And that is about that. But what if we have the perfect, we ran the algorithm, now we have the perfect calibration, the perfect predictions for every subpopulation. Now we have some issues that we encounter when we actually try to use these predictions in practice. So usually the way we like to use these prediction models that we do, and you saw only a subset of them, in a small subset of them in one of the first slides, is to take the predictions and translate them into some sort of proactive intervention list for physicians. You can think about it as a spotlight to some extent on the population that is of the highest risk, and the doctor needs to focus on that population to proactively call them and do A, B, and C in order to prevent the bad outcome that we want to prevent. But this is not, it turns out that this is not so straightforward. So this is like problems that we actually encounter in practice, and I'll tell you a story about the process that we underwent in the last few months debating this problem. So say we have a physician, Dr. Jane Smith, who is a GP that is responsible for the treatment of almost 2,000 individuals. It's not uncommon for Clalit clinics. And say that we applied the cardiovascular prediction algorithm that we've discussed to about 1,000 individuals of the relevant age ranges in her clinic. And we estimate that she can proactively call and treat 30 patients who are at high risk for cardiovascular diseases. She has we have multiple such lists, so we can't include thousands of, 100 patients on such a specific list for a specific outcome. So here we estimate that she can treat 30 patients. But the question is, which of the patients should be included in that list? So you probably think, well, this is a pretty stupid question, right? We could just take the 30 patients of the highest absolute risk, and this will be the intervention list for that physician. But once we do that, this list seems a bit unfair. Why? Because if I'll color it, you'll see that most of the list is males, and you can see that the average age is pretty old. It's over 80 years. And is that exactly what we want to do? Is this fair? We felt that it's not so fair, and we felt that we want to give opportunity for younger individuals to be included in the list and for females to be included in the list. So what we did is to create a percentile of risk that is adjusted for both age and sex groups. Now the list seems much better, right? It has blue individuals and pink individuals, and we have younger individuals. We have individuals as young as 46 years of age. And we felt much better about this list. We felt that it's much more fair, and we ran along with this solution for a while. But then we consulted an ethicist that told us that he thinks there is a problem here. And what he said is, look, for example, on Mr. Stanley on the first list and on Mrs. Greer on the second list. They are both 75 years of age. Can we really justify including Mrs. Greer on the list instead of Mr. Stanley, because you see that he's not included in the second list, who has a higher probability of cardiovascular disease? Is that fair simply because she's a female and we want the list to be diverse? So we debated that for a while because we felt pretty strongly that the list should be diverse. It seemed really fair. But after a while, we really came to the understanding that we can't protect this decision. If we want to protect it, to prevent cardiovascular disease, we need to prevent it as efficiently as we can, and we need to treat patients of high risk. So basically, we kind of reverted the decision to calculate percentiles based on both age and sex, and we basically only created the percentiles based on age groups. And this is more defendable because if we want to maximize the amount of healthy life years that we can preserve with this intervention, we kind of think that the third option is the best because the third option has relatively younger age groups, but relatively high average absolute risk. So currently, this is the option that we feel most comfortable with. There are no textbook solutions. If anyone in this crowd, which is especially equipped to think about these kind of problems, has better ideas, we'll really be happy to hear. But this is currently the solutions that we're running with. So we talked about different kinds of unfairness. These are really the kind of issues that we are worried about in our daily work. And just to say that we are really, this is part of our collaborators. We really like to collaborate with different institutions about these kind of problems. Specifically, the work we've presented was done in collaboration with the Weizmann Institute and researchers from Northwestern. And again, if anyone in the crowd feels that he has some cool ideas of things we can do using our data and maybe further explore fairness issues, we'll be really happy to hear from you later on. So with that, I think, thank you.
Let's take one question for Noah and Noam. Anyone?
So this question of how you deploy models, in particular, how do you determine intervention, is very interesting for me. Because in some sense, risk factor is a proxy measure of intervention effectiveness. It may not, in fact, be the correct way to intervene. So kind of, can you expand more on how do you determine who are the right patients to intervene? Practically, like for example, do you do studies after you're on for a while, you know, what were the interventions that actually worked? Because it might be not possible to do it prospectively, but now that you have some retrospective data on intervention effectiveness, this can inform the way you select the cohort. Maybe it's not the highest risk people, maybe, you know, younger people are easier to intervene, or et cetera. And how does that all tie into fairness? Because of course, intervention by the doctor also has kind of the biases with which the doctors treat various groups. Thank you.
Okay, this is a good question. usually we divide different types of interventions. So basically with predictions, what we do is, as I said, turn a spotlight into individuals at high risk. We try to make the list as fair as possible, as you saw here. But basically what we say to the physicians in those kind of interventions is use the guidelines you already know, the interventions that are evidence-based, that we already know are recommended, and don't reinvent medicine. As opposed to other projects in which we do causal inference and we try to identify the proper intervention for the right patients for a specific decision. So these are like two different kind of projects. With predictions, we usually just try to focus already proven interventions, and in causal inference, we try to understand what's the right intervention to do. I would say that now, when we're deploying these kind of models, we constantly evaluate them in practice. So maybe in a few years, we'll also have evidence about the actual effect of creating the prediction model and turning that spotlight on a specific group of patients. But that is currently still work in progress. So you said one question, right? Okay. So thank you again.
All right. Our last invited speaker is Chelsea Barabas, who is a PhD student at MIT, where she examines the spread of algorithmic decision tools in the U.S. criminal justice system. She works with an amazing group of interdisciplinary researchers, government officials, and community organizers to unpack and transform mainstream narratives around criminal justice reform and data-driven decision-making. Formerly, she was the head of social innovation at the MIT Media Lab's Digital Currency Initiative, where she examined the social and political implications of cryptocurrencies and decentralized digital infrastructure. Let's give Chelsea a warm hand.
How are y'all doing? Good? It's been a long day, huh? Just stretch out a little bit. I'm super excited to be here. And today, I think it's rather apt that I'm the last of the invited speakers to talk, because what I'm hoping I can use this last half hour for is really to take a step back from, I think, some of the more detailed conversations we've been having around different strategies for rendering AI in the medical context more fair and ethical, and really ask a bigger question about what are the limits of the ways that we've currently framed the ethical stakes of AI in the field of medicine and also just more broadly. So my talk is going to be broken down into 4 parts. The first part is I really want to kind of give an overview of the role that the concept of bias has played in anchoring our conversations around what it means to develop fair AI. And then I want to offer a counter perspective on what is really the most important things we should be considering, and push back on the notion that bias and inclusion as its solution to that problem are the most important things for us to think about. And I want to explore that further by kind of looking at some historical examples that we have of other ethical failures that we've seen within the field of medical research before I come to the last section, in which I want to draw parallels from those historical examples to some of the challenges we're facing today when it comes to AI in the medical context. So over the last couple of years, I think some of the most high-profile studies that have really generated a lot of the interest in this idea of fair AI have come in the form of bias audits. These are usually audits of algorithms where we do side-by-side comparisons to look at how that algorithm performs on people who belong to different groups, usually along racial or gender lines. And these audits are really a part of a much longer kind of history of academic scholarship, which has tried to audit and kind of surface discriminatory practices across a wide variety of different fields, such as hiring and recruitment for jobs, access to medical treatment, and so on. I think probably the most famous of those studies was published by Marianne Bertrand and Sendhil Mullainathan in 2003, in which they sent out resumes to a number of businesses around the Boston area. Those resumes were largely indistinguishable from one another in terms of education levels, work experience, but the key difference were the names associated with those resumes and whether or not those names were associated with white people or black people. What they found was that resumes with black names associated with them received half as many callbacks as similar resumes with white names on them. Now, one of the authors of that study, Sendhil Mullainathan, recently authored an op-ed in the New York Times where he argued that in the age of algorithms, these types of bias audits are much easier for us to perform because we actually have the infrastructures in place to gather data that's relevant for asking these types of questions. And he took that one step further by saying that not only is it easier for us to surface these types of biases, but we actually have a unique opportunity to intervene and course correct those biases by identifying, for example, problematic proxies for things like race in the algorithms that we build. And he made this argument by basically reflecting on his experience doing the resume study in 2003 and comparing it to the work he's done recently in auditing a medical algorithm that's used to triage care for patients in hospitals. He argued that in the case of the medical algorithm, not only were they much more efficiently able to surface bias, but they were actually able to address those issues by eliminating problematic variables in their model. Now, there are a lot of problems that I have with the way that Sendhil outlined his arguments in that New York Times op-ed. I'm not going to go into those right now, but the reason I wanted to bring it up is I think it's emblematic of the broader conversation we're having today around what it means to build fair AI systems. I've just grabbed these headlines that have surfaced over the last week or two. And what you'll notice, I think, in all of them is that the idea of bias figures prominently in them. And also the idea that if we could address bias, AI could actually help us to build more inclusive and diverse organizations and societies more broadly. This idea is being embraced by a number of large tech players out there, such as IBM, who have started to invest a significant amount of resources in building what they consider more inclusive and diverse data sets for things like facial recognition algorithms, which have come under increased scrutiny as people have done bias audits of those types of algorithms. Now, in the field of medicine, these values of diversity and inclusion seem to be particularly important to uphold, right? Medical research saves lives. And we know historically that most of the clinical trials that have been conducted for life-saving treatments have been limited to white men who have been included as participants in those studies. So we might think of diversity and inclusion as a really important thing for us to think about as we move forward with more data-intensive forms of medical research moving forward. But what I find interesting is that at this very moment when studies like the one I just posted up there, which is from one of my colleagues at MIT, as these studies are coming out, we're also seeing a growing number of people expressing concern around this idea of inclusion as being the primary vehicle for rendering these systems more ethical. So up here, these are screenshots from a talk that Dr. Ruha Benjamin gave in the fall of this year at a workshop that was entitled, "Please Don't Include Us." In that workshop, Dr. Benjamin challenged the notion that people of color and women are excluded from these systems. What she argued was that, in fact, oftentimes, these people are not only included in the systems that we build, but they also serve as kind of the bedrock for the innovations that we end up building over time. And facial recognition technology is a case study that she pointed to as a really good example of why we should be wary of this idea of inclusion. So her critique stemmed from this idea that for any technology we build, there's going to be a bifurcated market of products that are going to be distributed across the society that embed those technologies, and that one person's consumer technology is likely to be another person's carceral technology. What I mean by that is a technology like facial recognition for many people is going to be used to give them a more seamless or convenient consumer experience. But for other people, the way that they're going to feel or experience that technology is going to be the result of embedding it in things like police body cameras, and ultimately be used to increase their surveillance and processes of criminalizing them over time. In addition to those types of concerns, there are also a growing number of controversies around the way that tech companies are starting to approach or create efforts to actually include people in their systems. So a few weeks ago, Google came under fire for hiring contractors in the city of Atlanta to go out into the streets and actually try to incentivize people to provide a 3D scan of their face to include in their facial recognition database. Now, the reason that they made headlines was their primary tactic for getting people to participate was to offer homeless people, and in particular homeless people of color, $5 gift cards for their participation in this effort. Now, Google did this partly in response to calls for them to make their data sets more diverse down the line. But what they ended up doing was kind of showing the exploitative nature of that relationship or the terms of that inclusion down the line. So I bring up these examples because I think they're emblematic of this broader sentiment that is starting to be expressed by a variety of artists, journalists, and scholars who claim that woke AI, or AI that is primarily focused on helping us to de-bias our lives in various ways, is really not the end of the conversation. It's really just the beginning. It's not enough for us to simply conceive of algorithmic fairness just in terms of bias, because we have to understand the ways that marginalized groups are already included in these systems. And in fact, if we want to really grapple with the ethical stakes of these systems, what we've got to do is ask a more basic question of who stands to gain and who stands to lose from the innovations that we're generating from this technology. And in order to unpack that question, I think we have to take a closer look at the social relationships that undergird the innovations that we're striving for with data-driven research. Now, some of you might be asking, okay, how does this apply to medicine? Like, as I said before, in the medical context, it seems like, inclusion is really important. And I think that is both true, but also not the end of the story. And in order for us to really gain a full perspective of what the ethical stakes are in this domain, we have to unpack a couple of really key concepts and their relationships to one another. The first is the relationship between inclusion and extraction. And we're going to look at a case study to kind of like unpack what the relationship might be between those ideas. The second is the relationship between innovation and exploitation. Who is it that ends up benefiting and who ends up suffering as a result of the innovations we generate? And then the second is this idea of naturalization. What are the ways that we end up naturalizing these coercive or exploitative relationships and generating blind spots that make it hard for us to see that when we're trying to help someone, we're in fact actually hurting them down the line? So to unpack those big, heady ideas, I think what we need to do is, maybe look back on a historical example that I think probably everybody in this room is familiar with, at least on some surface level, which is the Tuskegee syphilis experiment. Raise your hand if you have ever read about Tuskegee in your IRB and human subjects. Yeah, like most of us, right? So it's a really interesting example. It really started in its important conversations around ethical practice within the field of medicine. It's a study that was a huge undertaking. It went on for 40 years, from 1932 to 1972. It became infamous because it was a study in which life-saving treatment was denied to the participants under the study who enrolled under the premise that they would be receiving treatment and care for their ailments. The study was limited to 600 African-American men. And it's important to note that the study actually started off as a clinical trial. So it started off with a set of researchers going out into the rural South, administering treatment to folks. But as resources started to dry up for their treatment, they actually pivoted the framing of their research. And what they noted was that while they were out in the field, that there were a large number of African Americans for whom there was no access to treatment or care. And rather than framing this as something that a call to action for, bridging the gap in access for these people, what they did was they framed it as a unique opportunity. It was an opportunity to study what they called the natural history of the disease. And they proposed a study whereby we would track and monitor how syphilis developed within the human body from the beginning of the disease to the end. It's important to note that a number of life-saving diagnostic tools and treatments did end up coming out of this work, in addition to a large number of academic studies. So, journal articles. So 13 or so articles were published from this work. We developed new ways of standardizing diagnostic tools, but it came at a very high cost, right? Hundreds of people died as a result of this, and dozens more of the family members of the participants went on to be infected as a result of this untreated ailment. But this was seen as an acceptable collateral damage because what it did, in the eyes of the researchers, was it set up the United States as being one of the preeminent places for cutting-edge medical research that ultimately would save more lives down the line. Scholar Britt Russert argues that the way that researchers were able to continue with this work and feel okay about it was that they depended on perceptions about what she called the primitiveness and the timelessness of Black Southern life to obscure the exploitations of the experiments that they were doing. The Tuskegee researchers referred to Tuskegee as a rural laboratory, they designed their experiment to extract data from the bodies that occupied what they called the rural laboratory. And in this way, they were able to characterize a deeply interventionist study, a study in which care was denied to people through active deception, as simply an observational study in nature, a very passive study that was non-interventionist at its core. Now, Britt Russert argues that we should see Tuskegee not as an exception, but much closer to the rule when it comes to medical research, which is a rather bold claim. But she claims that medical innovations have routinely taken advantage of and benefited from the racialization and underdevelopment of space. And I think that's a really key idea for us to think about as we think about what does it mean to design cutting-edge studies moving forward. Just case in point around this being kind of the rule, not the exception, there are a number of other studies that were funded by the same governmental organization who funded Tuskegee that were actually conducted abroad on even more vulnerable populations. So mental health patients, indigenous communities, indigent individuals living abroad in places like Guatemala. And in these situations, the researchers not only left the illnesses untreated, but they actually actively would infect people with the diseases so they could have the opportunity to study them down the line. Now, I bring these up really because I think they highlight, a few really important trends and challenges that we need to think about as we start to move forward and thinking about the role that AI plays in pushing medical research moving forward in the future. And the first is this idea of there always being a bifurcated market for any of the technologies we build. One person's consumer technology is another person's carceral technology. The second key idea, I think, is around this idea of data extraction happening under the guise of care. What are the ways that we end up including people or taking data from folks, but using these narratives of care and treatment as a means of doing that? And I think finally, what are the ways that we end up naturalizing or making ourselves comfortable with exploitative practices so that we're comfortable with this down the line? Now, I want to try to apply those concepts to a couple of case studies really quickly that are coming up, I think, as we see more and more research that involves AI in the medical field. One really interesting one, I think, is this idea of vocal biomarkers. So vocal biomarkers have this amazing potential to really render like diagnostic tools for things like Parkinson's more accurate and efficient and effective down the line. And so there's a lot of really interesting work that's being done in this space of creating vocal fingerprints of folks and trying to run new types of diagnostics on top of them. But at the same time, those same methods are being used in ways that are frankly kind of bullshit. Not kind of bullshit, completely bullshit. So there's a company right now who's trying to work with the Trump administration to develop risk assessments for asylum seekers who are seeking asylum at the US border. And they claim that with very similar methods, they can identify potential terrorists or potential criminals who are seeking asylum in the US border. And they claim they can do that with up to 97% accuracy, which anybody who's done any research in this space knows that's a near unattainable level of accuracy. So I think there's a lot of snake oil going on in terms of people seeking to profit from, I think, exciting and legitimate methods that we find within the field of healthcare, but applying it to other domains. As the market for biomarkers, vocal biomarkers starts to grow, we're also starting to see pretty serious practices around data extraction happen. So about 8 or 9 months ago, there was an expose which revealed that a company called Securus has partnered with jails across the United States to basically collect vocal prints from people who have been jailed. And the participation of the people who have been jailed is required in order for them to access the phones that are in the jail to call their families or their lawyer. So it's pretty coercive conditions under which people's vocal prints are being captured. These companies are then going to, basically their model is that they're a data company. They take that database of voices and they go and sell it to other for-profit companies who use them for a variety of different types of product development. Another really interesting example that I think is even a lot more nuanced is a recent announcement that the Gates Foundation, along with the National Institute of Health, made just a few weeks ago, in which they committed to spending at least $200 million on research for gene-based cures for sickle cell and HIV. And they acknowledge that both traditional gene therapies and genome editing approaches like CRISPR have historically been prohibitively expensive for the vast majority of people who suffer from these diseases. And they said that they hoped that this investment in this research would offer opportunities to bridge that gap. Now, researchers within these fields have both acknowledged their excitement about this large investment of money, but they've also expressed concerns around how this might actually end up exacerbating the divide between the haves and have-nots when it comes to these types of life-saving treatments. And at their core, some of these researchers have asked whether or not we've invested in the right set of priorities when it comes to actually addressing these diseases. And they pointed out that there are a number of life-saving treatments that are already available today, but which have not been tested in places like sub-Saharan Africa, where the vast majority of people who suffer from these diseases live. So the question is, should we be spending millions, hundreds of millions of dollars on kind of data-intensive research agendas, or should we be spending that money on trying to bridge that gap and include folks in testing and kind of increasing access to treatments that we know already work? So I just bring up these case studies because I hope that they can start to point us in a direction to start to think about a set of issues that I think up till now have been pretty much neglected in the conversation about what it means to develop ethical AI in this space. And the first thing I think we've got to do is we've got to acknowledge that bifurcated market for technology and start to look for ways that our research is being used and weaponized for carceral purposes. Once we acknowledge and start to identify them, I think we need to start to actively resist those applications being used. And I think the Tech Won't Build It movement is a great starting point for those types of conversations. A recent poll in the United States showed that the average American trusts the builders and developers of technology to be the people to identify what are acceptable and unacceptable uses of those technologies. So I think the people in this room are the ones who really are going to have to be the leaders in resisting unacceptable or carceral uses of their technology. And I hope that we start to see more people from the academic world actually participating in that. I think a good example of that is a recent Manifest No, which was put on my radar just this week, which was published by a set of academics who I think do something really interesting. They both actively acknowledge and refuse what they call harmful data regimes, or these harmful uses of technology. And they also make a set of commitments for what it would look like to reimagine these types of relationships that undergird data-intensive research moving forward. So just in summary, I think I'd like to say that my hope from this talk is that we can start to expand the conversation to beyond just thinking about bias and diversity and inclusion, and really think about ways that we can both resist harmful applications of these technologies and extractive data practices, while at the same time reimagining what it would look like to build more accountable research relationships and think about what it really means to include people in terms that would actually benefit them down the line. Thank you.
Let's take one question for Chelsea.
Chelsea, that was fantastic. Thank you so much for this awesome presentation. The bifurcation sort of narrative that you're describing seems to also parallel something that I'm noticing within the conversation, which is there's this one track that talks about or imagines the mathematization of fairness, where you sort of debias a model based on this percent, versus sort of moving from fairness to justice. Mm-hmm. And I'm very curious to know what your experiences like have been in this conference and in other settings in which these conversations with specifically machine learning engineers like us who are looking for concrete ways in which we can sort of, implement sort of those values and systems, or try to build more ethical systems in a field like medicine that is already, as you have very eloquently described, historically biased and racist, and in that setting. And I wonder, are there ways, or are there technical ways in which you've seen that, those sort of maybe recommendations that you provided to engineers, or is that just not possible in that space? And I'm really curious to know what your thoughts are on that.
Sure. I mean, so with regard to the immense effort that's been put into kind of trying to formalize definitions of fairness, which I know different people have been trying to poke holes in and kind of complicate, what I found with a lot of those conversations is that they're at a certain level that doesn't really probe into the underlying assumptions that shaped how we even understand what the problem is and then conceive of what the potential solution is. And so I think, risk assessments are a great example of that, right? There's been a lot of conversation around how we render risk assessments less biased, and there's been less conversations about whether or not the terms in which we talk about risk assessments are valid, whether or not we can actually measure public safety risk by looking at arrest records and things like that. So the thing that my hope for technical communities is that they start to develop a vocabulary that helps them kind of go a couple layers deeper in conversations, so that they're able to kind of come and critically kind of engage with how people have framed the problem that they're trying to solve, and then how they think about the solutions. And I think a key part of that is understanding who do we work with. I think in general, folks don't give a lot of consideration to who they consider their end user. We want to make user-friendly technology, but we don't ask hard questions about who our users should be, or who they who they can't be because they don't have the resources to actually benefit or invest in these types of technologies. So in the case of, technologies that are built in partnership with government, I think that's really, really important. And a lot of care should be put into thinking about when those relationships are useful and when they could actually end up doing more harm than good.
All right,
done?
let's thank Chelsea again. We have a break for about a half hour. We'll gather back at 4 for a panel discussion and hopefully more opportunities to ask questions.